to this Engineer L. Venkatakrishna Iyer, Engineer KV Srinivasa Rao, and Engineer ML Swami 23rd Endowment Lecture. In the year 2001, then erstwhile Andhra Pradesh State Central Committee had unanimously resolved to organize an endowment lecture annually at State Center in honor of great engineer, statesman, Padma Bhushan Engineer L. Venkatakrishna Iyer, former chief engineer in the composite Madras State and past chairman IEI AP State Center, Engineer KV Srinivasa Rao, former chief engineer, irrigation and past chairman IEI AP State Center, and Engineer ML Swami, former engineer-in-chief, irrigation and CAD department, who have rendered immense services to the erstwhile state of Andhra Pradesh in the irrigation and power sectors. Accordingly, the State Center of IEI is organizing the above endowment lecture every year. I am glad to inform that the Telangana State Center of Institution of Engineers India has been regularly organizing endowment lectures totaling to 20. So they are Engineer V. Subbarao Endowment Lecture, Engineer M. Tirupati Reddy Endowment Lecture, Professor K. Gopichand Endowment Lecture, Professor J. Purushottam Endowment Lecture, Engineer G. Padma Prabhakar Endowment Lecture, Engineer Koka Krishnamohan Rao Endowment Lecture, Engineer G. V. Subbarao Endowment Lecture, Engineer T. Hanumantarao Endowment Lecture, Engineer A. P. Ranganatha Swami Endowment Lecture, Dr. S. Raghavachari Endowment Lecture, Dr. Narla Tatarao Endowment Lecture, Engineer Matur Gopal Rao Endowment Lecture, Engineer Gurram Kotreddy Endowment Lecture, Engineer Atturi Venkateswara Rao Endowment Lecture, Engineer R.L. Razu Endowment Lecture, Dr. Jan A. Murray Endowment Lecture, Dr. N.V. R.L.N. Rao Endowment Lecture, Engineers L. Venkatakrishna Iyer, KV Srinivasa Rao and ML Swami Endowment Lecture, which today we are going to organize. Dr. A. Ramakrishna Endowment Lecture and Engineer I. Basavarazu Endowment Lectures. The endowment lectures are being delivered by people of high eminence with considerable professional experiences to throw lights on important emerging topics of today's relevance. I take this opportunity to say a few words about great engineers, late Engineer L. Venkatakrishna Iyer, Engineer KV Srinivasa Rao, and Engineer ML Swami. Engineer L. Venkatakrishna Iyer served as chief engineer in the composite Madras State and retired on May 7, 1943. He was associated with Nagarjuna Sagar project, originally taken up as joint venture of Andhra Pradesh and Hyderabad states. When the Andhra Pradesh came into existence in the year 1962, he was elevated as secretary to government PWD. At the ripe age of 88 years, he is a past chairman of the Institution of Engineers India, Andhra Pradesh State Center. He was the recipient of Padma Bhushan Award for his meritorious work. Engineer KV Srinivasa Rao joined the PWD as assistant engineer in the year 1939. He worked in various positions as assistant engineer, executive engineer, and superintending engineer in irrigation department. He became as chief engineer in 1962. Later, he was promoted as member, Central Water and Power Commission, Government of India. He was appointed as chairman APSCB in 1972 and retired in 1974 with an outstanding record of service. He was past chairman of IEI AP State Center. He undertook many major irrigation projects and responsible for many power projects of AP. Coming to Engineer ML Swami, he served in the erstwhile state of Andhra Pradesh in various capacities in Krishna and Godavari deltas, Vamsadhara project, Srisailam project, Nagarjuna Sagar project, and various other medium and minor irrigation projects. He also served as project engineer in the erstwhile AP State Construction Corporation and general manager of National Hydroelectric Power Corporation, New Delhi. He retired as engineer-in-chief, Government of AP in 1983. Today, we have arranged Engineer L. Venkatakrishna Iyer, Engineer KV Srinivasa Rao, and Engineer ML Swami 23rd Endowment Lecture on the theme Simulation of Selective Water Resources Engineering Applications. Since you are anxiously waiting to hear the talk from our keynote speaker, Dr. N. Suresh Kumar Garu, I am limiting myself and hope that you will really enjoy his talk. On behalf of the Telangana State Center of IEI and on my own behalf, I once again extend a hearty welcome to keynote speaker Dr. N. Suresh Kumar, Professor, University College of Engineering, OU, and all of you to this important event. Thank you, one and all. Now I request Engineer Rama, convener of the event, to introduce the speaker to the audience.
Good evening, sir. It's a kind privilege for me to introduce our keynote speaker, Professor Dr. N. Suresh Kumar Garu. He's a professor from Department of Civil Engineering, Usmania University. He completed his BTech in 1985 from Kakatiya University and ME from Anna University, Madras in 1988 from Irrigation Water Management. Professor Dr. N. Suresh Kumar Garu obtained his PhD degree from IIT Bombay in 1998 for his work entitled Jet Mixing in Flocculations under the guidance of Professor Dr. B.S. Pani Garu and Professor Dr. S.G. Joshi Garu. He has more than 30 years of teaching and research experience. He transferred the technology developed as a part of his PhD program from lab to land, provided the process design and drawing for a jet flocculator, a component in primary treatment unit of kitchen effluent treatment plant for Annamrita ISKCON Food Relief Foundation, Mumbai. The project site is located at Kanched village near Wada, Maharashtra. He has published 10 national and international journals and more than 20 in international and national conferences attended. He has delivered more than 30 guest lectures in reputed government and private institutions. Thank you, sir. I request our Dr. Professor N. Suresh Garu to continue the lecture.
Yeah, thank you for your kind words. Good evening to all the organizers as well as the participants. So I will begin my lecture. So basically, simulation is the art of executing an activity without having to go for physical modeling. So simulation models generally make use of mathematical equations to represent the physical process that is involved in the problem. So here, these simulation models can be adopted for a wide variety of purposes where safety is a concern, or for example, where a specific activity cannot be performed because of safety concern. Under all such circumstances, simulation can be adopted. Coming to civil engineering water resources application, it can also be performed in water resources area. For example, you wanted to predict the scenario when a dam breaks. So what would be the effect of the inundation at a specific distance from the breach point, or what is the depth of flow from the breach point? Under such circumstances, also one can go for the simulation models. Why? Because simulation models are generally easy to use and compare. The results which are being obtained from the simulation models can be compared either with experimental results or with analytical results. Or sometimes if both things are available, one can even think of comparing with both the things. So the disadvantage with physical modeling is that you need a lot of manpower, water, energy, resources, and even instrumentation. All these things can be avoided if you go for simulation models. So in case of simulation models, so this is basically is being done through computational fluid dynamics. So it's one of the alternatives to the physical modeling. So what is being done here is because they make use of Navier and Stokes equation. So they are second order nonlinear partial differential equations. So direct solution is generally not possible unless and otherwise the convective terms vanish on their own because of the boundary conditions that are imposed upon the problem. So the governing equations are given here. So these are the governing equations which are being used in the modeling aspect. So here there are actually 3 momentum equations and 1 continuity equation. And so that means 4 equations are there and even 4 unknowns are also there, like velocity component along x direction, velocity component along y direction, velocity component along z direction, as well as the pressure term. So 4 equations and 4 unknowns, there is no problem as long as the flow is in laminar state. But when it comes to the question of turbulent flow, there are additional terms which are coming into picture. That is primarily because of the fluctuating velocity components. So they are u prime, v prime, and w prime. So the number of unknowns have actually become 7, whereas the available equations have become only 4. So to cope up with this kind of scenario, what is generally being done is these fluctuating velocity components are expressed as a function of mean motion so that the problem can be solved. This is what is called as closure problem. So closure problems basically make use of the turbulence models. 2 of the popularly used turbulence models are K epsilon and K omega. The equations of K epsilon and K omega models are given here. So each of these terms on the left-hand side as well as right-hand side, they represent, okay, what is the rate of change of kinetic energy or energy dissipation or transport of Kr epsilon by convection or rate of change of Kr epsilon, rate of change of destruction of K or epsilon, and transport of Kr epsilon by diffusion. So in case of simulation models, it consists of 3 stages. One is pre-processing, other one is processing, and third one is post-processing. In pre-processing, one has to create the geometry. That means as it is, whatever the physical structure that is available, it has to be drawn to a suitable scale. Generally, scale models are being adopted to create the geometry. So depending upon the size of the model, an appropriate scale model can be selected. So it can be, there are different softwares available. One can even do it in AutoCAD, okay, or else Design Modeler, okay. So that can be imported into the software. So ANSYS CFD is one of the popularly adopted software for CFD purposes. So later on, one has to do meshing. So that is, meshing is generally being done in order to discretize the flow field. Then from there, you go for the processing. In the processing, there are different solvers. And after making use of the solvers, then you go for the post-processing wherein the results will be indicated. So the different solvers which are being used in the processing stage are given here briefly. There are 2 types of solvers. One is pressure-based solver and the other one is density-based solver. Basically in civil water resources engineering applications, we make use of these pressure-based solver because density generally remains as constant. So either one can go for segregated algorithm or coupled algorithm. Generally, segregated algorithm is being adopted. The reason being, so the equations, governing equations, that is continuity equation as well as momentum equations, they are being solved in a sequential manner rather than simultaneously. So these are some of the popularly adopted models like simple semi-implicit method for pressure linked equations, or otherwise PISO is also being adopted. So which of course takes little less time. So the algorithm that is being adopted in case of simple is given here. So what one needs to do is you assume some pressure field, then solve for the momentum equations as well as velocity components, then update the pressure field and substitute in the continuity equation, then solve for the turbulence models. If the solution has converged, then there is no problem. Otherwise, you apply the updated pressure correction to the initially assumed pressure field. So this process goes on in an iterative loop till the solution is going to converge. So what happens is most of the time, or at least some of the times, the results which are being obtained from the simulation models are not directly readable. So they only provide qualitative information. They will not give you the quantitative information. Under such circumstances, one has to go for what is called as user-defined function. So a user-defined function is generally programmed in a C language, and it can be loaded into the software, ANSYS Fluent software, to get the quantitative information. So some of the features are given here, which one can program in C language. So it has to make use of a UTF.h file. Then it has to be loaded into the software so as to get the desired information. So that is what is being done when you are actually the quantitative information is not available from the output of the software. So here I am giving some of the case studies which can be thought of in case of irrigation or water resources engineering applications. So one of the application is where is the impact point when water glides over the spillway. So you wanted to predict the location of the impact point from a ski jump bucket type arrangement. So that is being shown here. So it has been taken up with all these objectives. You wanted to compute the velocity as well as depth of the flow along the flip bucket, then trajectory, jet angle as it leaves from the spillway bucket, dynamic pressure, maximum pressure, what is the distance of jet through, as well as height above the center line of the lip level of the bucket. From the lip level of the bucket to the center line of the trajectory, what is its height? So one has to calculate these things. So generally, to evaluate these parameters, normally physical modeling is being done, but here we have gone for the simulation. So the case study that has been taken was Nagarjuna Sagar Dam. So the salient features are given here. So the data has been taken from the irrigation department. So this is available on the website. So because most of the audience are basically field engineers, so they may be knowing all these details much better than me. So what we have done for the spillway profile, we have adopted USBR waterways experimental station. So this is the equation that has been given by them. Then we have computed what is the fruit number, and when you know the value of fruit number, you can actually evaluate what is the angle of the bucket angle at the lip level of the bucket. That alpha j can be computed making use of the value of the fruit number. Then in order to compute the maximum pressure in the bucket, so these two equations have been used. One is Gomenski's equation and the other one is Balofet's equation. Here, VA is the velocity of approach, actual velocity of approach. But if at all you wanted to get the actual velocity of approach, actually one can only get the theoretical velocity of approach if you know what is the head over the spillway crest, as well as what is the height of the crest. From that, you will be able to compute. An equation is available in the literature. So based on that, one will be able to compute what is the theoretical velocity. But in the literature, one chart is also available. What is the ratio between V actual and V theoretical? So that ratio can be obtained from the chart, which is available in the literature. So that is how one will be able to compute the value of V actual. So knowing the value of V actual, so one will be able to evaluate the value of HD. Okay. Then what we have done is, in order to evaluate the location of the impact point, so we have proposed these two equations. So these equations are actually not available in the literature. So we have proposed these two equations based on the trajectory of the jet. So what is the location of the impact point from the spillway bucket out edge point, as well as y is taken as the height from the lip level of the bucket to the center line of the trajectory. So these are the equations which we have proposed. And these equations have been evaluated from the simulation. From the simulation results, we have actually proposed these two equations. So first, what we have done, because whatever the result that we are going to get, we were not sure. So what we have done first, we have made analytical estimates. So this is the bucket of the spillway. So D0 is the depth of flow at this point. D1 is here, and D2. D1 is basically at the along the middle. D2 is here. So here, what one needs to do is, what is the energy of the flowing water on the upstream side. So you apply energy equation on the upstream side, as well as, let us say, at this location where you are willing to compute the value of D0. So from continuity equation, Q is equal to area times velocity. So you know what is the value of the discharge per unit length of the spillway. Capital Q divided by L will give you small q. So small q divided by D0. So you will be able to express the velocity in terms of Q by D. So that is how, so the energy on the upstream side is available, energy on this is available. So like that, you equate to at D0 and D1 or D1 and D2. So like that. So one has to obtain the values of depth of flow in terms of Q. So by a trial and error procedure. So that is how we have got the values of D0, D1 and D2 by adopting a trial and error procedure. So knowing the value of depth of flow, then we have computed velocity. So velocity is Q by D. So at these three locations, we have applied energy equation and have got these values of depth of flow as well as velocity. Then other parameters, like fluid number, pH, and what we have done, we have actually evaluated for what is the maximum discharge, design discharge, 75% of the maximum discharge, 50% of the maximum discharge, as well as 25% of the maximum discharge. So the depth of flow, then what is the invert level of the bucket, then lip level of the bucket, then what is the trajectory angle. All these values we have computed for different flow rates. Then dynamic pressure has been computed from half rho u v square, half rho u square, and maximum pressure at the invert level of the bucket has been computed from either from Gominski's equation or Balofet's equation. So these are then the through distance as well as the height of the trajectory jet, they have been computed with the equations that have been proposed by us. So then these are all analytical equations. Then we have gone for the simulation. So the dam, that means Nagarjunasagar dam, has been actually drawn to 1:100 scale. So then the boundary conditions are, we have given the velocity inlet. So that means what is the velocity with water is approaching the over the crest of the spillway. And because on the top as well as downstream side there is atmospheric pressure, we have defined it as pressure outlet. Then we have gone for the meshing. Then what we have done in order to reduce the CPU time, actually, so we have initialized the flow condition. That means we have filled up water on the upstream side of the reservoir up to FRL, and then we have started the simulation. So here, this is the water surface profile as it glides down the spillway. So we have extended our simulation process till it reaches to the downstream end of the structure. So here from the output of the software, you only get this kind of information. That means qualitative information. Here, red color represents water as well as blue color represents the air. So this is a multi-phase problem. So, but it will not give you what is the value. So it is for that purpose, actually, we have gone for the UDF, user-defined function. So that is how we have evaluated what are the values at different sections all along. This is from the axis of the spillway we have taken. So here, this is the spillway edge from the top of the lip level of the bucket up to the center line of the trajectory. This has been taken as Y, and from the spillway edge to the impact point has been taken as the X value. So that is how we have computed what are the values of these trajectory jet all along its length as well as height. And here, so the velocity magnitudes one can see here over the crest of the spillway. Actually, this is the enlarged version over the crest of the spillway. One can see here, actually the scale is not clearly visible. Here there is negative pressure, but that negative pressure is not going to extend down the spillway. As it comes, there is increase in velocity, and here it is even more in the flow velocity has gone down. It has, that means the flow velocity has increased further. So there is no problem that this is likely to extend because it's only for a minor region. This is also being corroborated with the information that is available in the literature also. Then contours of dynamic pressure. So this is the spillway bucket. This portion. So we have computed what is the maximum pressure in the spillway bucket. So we have evaluated all these values from the simulation. What is the depth of flow in the bucket, through distance, height, and dynamic pressure in the bucket, maximum pressure at the invert level of the bucket. All these values have been evaluated from the simulation results. So one can see here, there is this the analytical velocity, of course, because it has been adapted to a 1:100 scale. When you convert, so that's how it has become 0.8309 simulated velocity. So here is the comparison between the computed depth of flow for D0, D1, and D2 and simulated flow. Hardly there is any error. The error involved in the process is less than 1%. And even velocities also, there is not much variation. Then, so this is trajectory jet angle at the lip level of the bucket. This is the computed value. This is the simulated value. Error percentage is also less than 1%. Then dynamic pressure in the spillway bucket, computed value making use of analytical equations, simulated values making use of the software. Error percentage is always less than 2%. Then these are maximum pressure in the bucket according to Gominski's as well as Balafet's equation. In both cases, in Gominski's, the percentage of error is less than around 1.5. Here there is negative percentage of error, so amounting to approximately 5%. So then ultimately, this was our key point of interest. What is the distance of jet through as water glides over the spillway, in case of ski jump bucket type arrangement? So there is hardly any error between for different flow rates. This maximum design discharge 75% of the design discharge, 50%, 25%. In all these cases, the computed value is based on the equation that has been proposed by us, making use of the trajectory jet theory, and simulated values are the values which have come from the software. Similarly, even for height also we have computed. There is hardly any error. So this is one of the first application. Then the second application which we have gone is flow bifurcation into lateral channel. So that means whenever, let's say, water is to be let out to lateral channels, how the flow, that means you need to discharge your intended flow into the channel, lateral channel. Generally, what is being done is, in case of flow into the lateral channels, a vertical lift gate, a mechanical arrangement is being provided. So to work on that, we have so this is the general arrangement. Water goes from main canal to the branch canal, then branch canal to minor to then outlet. So these are all you are very much acquainted. So basically, one has to see that the intended discharge should go into the lateral channel. Then only the problems in the command area can be averted. Otherwise, the farmers in the command area will always say, we have not actually got our intended share of flow rate. As a result, there are disputes. So to overcome that problem, actually, we have gone for a simple, okay, system without any kind of mechanization in the process. So this one of the author who has actually studied what kind of alignment should be made for the lateral channels, okay. So he has proposed that acute angles, okay, should be not be encouraged. So what is the objective of this present study is that we wanted to develop a simple and efficient ungated system so that mechanical arrangements can be avoided. In the process, we also wanted to ensure that the design flow rate should go into the lateral channel. So we have taken the case study of Nagarjuna left bank canal, okay, Rajapuram major distributary. So this is the input data. So this is the flow rate, bed width, full supply depth, and velocity. And we have taken one of the minor. So the intended flow rate into the minor was 0.169. So in the existing system, this is the alignment. So the lateral is being aligned at 90 degrees to the main canal. And what is being done is the bed level of the major distributary as well as minor distributary are at the same level. As a result, what is happening is the liquid level in the minor is dropping significantly. So how much means what is the difference in depth of flow between the distributary and minor? By so much amount, the liquid level in the minor is coming down. Because water is available at a lower level, obviously the area that is going to be commanded by the system is going to be on the lower side. So to overcome this problem, what we have proposed is instead of 90 degrees alignment, why can't we make it in 110 degrees alignment? Because the logic is very simple. When you wanted to take a turn on a road, if you have a 90 degrees turn, it becomes difficult for you to take a turn. On the other hand, you have 110 degree alignment. So one can easily go without much difficulty. So in order to see that the water passes easily, in case of 90 degrees alignment, what is happening is it is becoming harder for the water to enter into the lateral. So to overcome that problem, what we have done is we have made the alignment of the minor with the axis of the distributary as 110 degree alignment. And not only that, because the area that is being commanded by the system is coming down, what we have done is we have proposed to map the liquid levels of the major distributary as well as minor. So we wanted to keep the same free surface level in both the systems. So that is how we have actually raised the bed level of the minor. So how much means whatever the difference that is there between the flow depths, by that much amount we have raised the bed level of the minor. So what we have done, first we have analyzed the results. These are the results of the distributary, major distributary for full supply as well as half supply. So these are all constants. So one can get it according to the data that is available. So we have even computed the values for the L1 minor. So here, because in case of the existing system, there is actually a mechanical arrangement is available. Yes. Yes, there is any query. I have no problem in answering the queries even while my presentation also. Here, there is a tower head and a vertical lift gate is provided here, which will be operated from this tower head. So if you calculate what should be the amount of gate opening corresponding to the flow rate, corresponding to the flow rate you wanted to release into the lateral channel, accordingly, this gate opening has to be computed and it has to be kept, whether it is for full supply or half supply. Accordingly, the gate opening has to be computed and accordingly it will have to be operated as per the requirement. So obviously, because the gate opening is being computed as per the intended flow rate, so you are likely to get the desired result. That means whatever the flow rate you wanted to allow into the channel, that will go into the channel. But only problem is one should not mishandle the system after the line organization staff goes off. So what we have done is, instead of a mechanical arrangement, we have proposed a rectangular notch. We have proposed. And what is the length of the rectangular notch? We have computed for full supply flow rate, it has come as 14 centimeter, and for half supply, it has come as 16 centimeters. So the definition sketch is given here. We have actually mapped corresponding to the half supply flow rate, the liquid levels, both in the major distributary as well as minor, we have mapped. So that means for half supply flow rate, these FSLs are at the same level. So as a result, what has happened? The bed level of the minor has been raised by around 2 feet. So that means water is available at a higher level. So one can actually command a lot of area. Whereas in case of full supply, because you cannot actually change. So same, you wanted to map the same, because this 0.607 at the same level, because bed level cannot be changed once it is constructed. So for full supply condition, the liquid level has actually dropped by around 3 inches. So this is so what we have done, we have created this geometry, okay, in design modeler. So this is the geometry of the system. This is the main canal. This is the distributary, minor, sorry. This is the major distributary. This is L1 minor. And this is the close-up view of the rectangular notch, which has been proposed for allowing the intended flow into the minor. Then we have done for the meshing and the boundary conditions which we have given here. This is the velocity inlet, and here these are all pressure outlets. Then we have, okay, run the solution till the solution is going to converge, okay, for the all these parameters, continuity equation, velocity component, x, y, and z, as well as k epsilon, okay, till they come down to, okay, 1 into 10 to the power minus 5, below that. That is the acceptable criteria for convergence. Till such time we have actually run the solution. And here the contours of volume fraction are indicated. So this red color actually represents the water and blue color represents the air. So this is the flow in the distributary, and this is the flow that is taking place in the minor. So we have actually evaluated what is the flow velocity in the minor and what is the depth of flow in the minor. So flow velocity, one can actually get it from the velocity contours as well as velocity vectors, which are available in the post-processing of the software. So you'll get it. So these are all the, okay, vectors of velocity magnitude, indicating even the direction also. So then we have actually computed the mixture area weighted average velocity. So this 0.3141 meters per second. So that is what is from simulated velocity. Analytical velocity I have already shown right in the beginning for L1 minor. So there is an error of 3.37. So velocity one can actually read from the software, but depth of flow cannot be obtained. For depth of flow, we have actually adopted a user-defined function, and we have actually evaluated. So that evaluated depth of flow, we have got it as 0.2032, whereas computed value from the, okay, analytical equation was 0.2041. So there is some error. And flow rate was, okay, there is an error of around 4%. This is for half supply. Similarly, we have even done the simulation even for the full supply also. So here also the amount of error is always less than 3% for the important parameters like flow velocity, flow depth, as well as flow rate. Then what we have done is, so what are the consequences if we actually go for the conventional system? When you go for 90 degrees alignment of the minor, or when you make the angle of alignment to 100 degrees or 110 degrees, what are its consequences? We have studied 3 important hydraulic parameters, namely flow velocity, flow depth, and discharge for both half supply as well as full supply. One can see from this table, the flow rate here was around 0.0812. If you go for 100 degree alignment, that intended flow rate is not actually entering when the alignment is in 100 degrees or even 90 degrees. For 90-degree alignment, it is even much lesser than 100-degree alignment because it becomes harder for the water to take a 90 degrees turn. Similar is the case even for full separate discharge also. So the intended discharge is being obtained at 110-degree alignment. That's the reason we have not gone for 120 degrees alignment. So this information is actually available in the literature. We have actually proceeded with 110 degrees alignment as the benchmark, okay, that is available in the literature, and it has been proved to be correct. Then similar design concept also we have, okay, applied for a water treatment plant, wherein the water has to enter into two different lateral channels. So the case study which we have taken is a water treatment plant that is available near Nagarjuna Sagar, Kondapur, okay. So the flow rate, okay, into each channel is 0.784. So the definition sketch, so this is the existing system. The proposed system is same 110-degree alignment. We have proposed two lateral channels. So there is a, from flash mixing chamber, water is actually entering into those two laterals through a vertical lift gate. So what we have done is, instead of going for a vertical lift gate, so we have provided a rectangular notch. Here in this case, what we have done is, by how much amount the crest level of the rectangular notch should be kept above the bed level of the lateral channel, and what should be the length of the rectangular notch. These things we have actually obtained by trial and error procedure always. So length of the rectangular notch has been obtained as, okay, 0.028 meters, and the crest level of the rectangular notch should be about, okay, 9.1 centimeters above the CBL of the lateral. So this was the geometry which we have created in the, okay, ANSYS software for the two lateral channels. Then we have applied the boundary condition, what is entering from here, okay. So this is the inlet, or others are pressure outlets. Then we have done till all the required governing equations are being satisfied to a precision of 1 into 10 to the power minus 5 or below that. So this is the contours of volume fraction. Red is water, blue is air. So then we have evaluated what is the depth of flow from user-defined function, as well as flow velocity. Of course, one will be able to get it from the vectors itself. So there is no problem, as it is software will give you directly. So the flow velocity has come as 1.33 meters per second, whereas analytical value is 1.32. So percentage of error is always less than 1%. So in this endeavor, okay, I thank both my research scholars, Ms. Prasanna as well as Sri Ramya. Both of them actually, they have helped me in the solution of these complex problems. So I thank all the audience for their patient listening, and I'm open for the discussion. Thank you.
apply kido kana RTA commission apply kidana కానీ అది ఇంతవరకు ఏం చేయలే.
Highly appreciable talk, Professor Saab.
Okay, thanks a lot.
Professor Ramna here. Ramna
yeah, I could able to see your face.
How are you, sir?
Any queries? Sir, any queries from the participants?
Yeah, sure. That is the reason we are kept open for discussion.
You go. Professor Ramna here.
Yeah, please.
Chairman Saab, sir, Suresh Saab, highly appreciable talk. While presenting your 3D pictures, all we want to go for one more talk on Medigada after a couple of weeks.
For that, no,
Thank you.
basically,
Thank you.
lot of input data is actually
Yeah,
required.
yeah.
So
Yes, sir.
then,
Yes, sir.
then it is
Yes, sir.
possible.
Good day, sir. Thank you, sir.
Okay, right.
Manala.
So if any of the audience has any point to take it forward for implementation on the field, so we welcome their views for the possible implementation on ground.
గుడ్ ఆఫ్టర్నూన్ అండి.
Good afternoon.
ప్రొఫెసర్ సురేష్ గారు చాలా బాగా చెప్పారండి. రిగార్డింగ్ 2 or 3 ఇష్యూస్. ఒకటి ఏంటంటే మనకు సిమ్యులేటెడ్ ఫ్లో, ఒకటి సిమ్యులేషన్, ఇంకోటి ఏమో కంప్యూటెడ్. మనకు మెజర్మెంట్స్ అవి ఉన్నాయి కదా. వెన్ ఇట్ కమ్స్ టు ద బకెట్ పోర్షన్, you have compared the simulated value and the main computed values, and you have
computed value is basically from the equation that is available in the literature. Right.
Can we compare it with the actual values on the field?
Yeah. So in fact, no, I would like to tell you one point over here. So what has to be done? Actually, we have taken for the flip bucket portion, the downstream spillway profile. Actually, we took it as USPR water-based experimental profile. So in the design document, which we have got it from the website of the irrigation department, they have actually given a different equation. My point is, if at all, to answer your query, so whether we can actually compare with the physical measurement, what one has to do is, what is actually the profile that is existing on ground at different orders. If one can map that profile, then it is possible to run for the simulation and predict what is the possible scenario that might result in with that kind of spillway profile.
So there is one aspect. Can we really physically measure the various parameters at the field level? Is it possible? What do you think?
For which case study you are asking, sir? For spillway or
for example, there is Nagarjuna Sagar spillway.
It is possible. For example, because when flow rate, let us say maximum flow rate is coming, so one will be able to know what is the impact location. So one can physically measure. One need not be precise enough. So one can mark from the band, so tentative location, and you can map even later on also. You can measure physically the linear distance.
Your conclusion that you have drawn the water into the distributor from a main canal. So the angle of taking it about 110 degrees is very innovative. It's really very useful. And I have observed I have observed is for the half flow condition and full flow condition, if we compare, for the full flow condition, you are getting double the flow.
No, actually, whatever because half
I got the point.
Half of the flow.
Yeah, I got the point. Yeah. So you are able to get the full discharge which is required.
Yeah, design
and
discharge.
It comes to about double the actual double the actual with 90 degrees when compared to 90 degrees.
Yeah.
110 degrees is double than that required for 90 degrees.
Yeah.
That's a very good innovation. The second one is for the water treatment plant. So what do you think is the advantage of your rectangular notch?
No, basically it's a non-mechanized system. So the cost of investment on mechanical arrangement can be avoided. Not only that, so this is actually a common problem in water treatment plant. Water treatment plant, what happens? There are many mechanical devices for in coagulation as well as flocculation. In fact, people, they even go for speed regulation devices also for flash mixers or for slow mixers. So when these devices are not being operated according to the season or according to temperature requirement, over a period of time, they actually become defunct and they may not be able to render service in the hour of your need. So it is always advisable to go for a non-mechanized system rather than going for a mechanized system. So in view of that one, what we have done is, why can't we think of a simple, ungated system which will avoid all mechanical components? That was the idea.
I got your point, but when it comes to this channel, we are having a venturi flume there usually.
Yeah, venturi flume is basically intended for measuring the flow rate. In
Yeah,
fact,
absolutely.
no, I have actually taken the physical measurement for that water treatment plant. So it is actually not okay as per the intended flow rates that we have actually presented over here. So that is the advantage with this kind
Oh,
of simple
so we are
arrangement.
avoiding any mechanical this thing equipment, etc. That's what you are saying.
Yeah.
So very good idea. So thank you very much for the wonderful, insightful, presentation. Very good presentation. Wonderful. Thank you very much.
Okay.
Sir, I have a small doubt, sir. What are the softwares used for modeling and also for analysis purpose?
So analysis, actually the equations, whatever that are available in the literature, same equations we have adopted, except for that trajectory jet location length as well as for the height of the trajectory. Those are the only two equations which have been proposed by us, because no, those equations are actually not available in the literature. So we have proposed in order to make the life of the field staff simple. But regarding the software, we have actually gone for ANSYS Fluent software, which is a commercially available software in the market. So for simulation, we have gone for that.
So those the equations you have developed are based on the continuity equations, is it?
No, that ski jump bucket, the length as well as height, we have actually adopted trajectory of the jet.
Okay.
Which is available in the literature. Okay, in any physics textbook you take it, so you will get that trajectory theory in the textbook. So we have modified according to our situation, so as to match with the simulation result. Actually, that is not available. From simulation results, we have actually compared and proposed those equations.
In fact, if you compare the trajectory length with the actual length at the field, the trajectory length at the field, that will be very, very insightful exercise.
Yeah, that I really appreciate that point. Only for that, the bottleneck is the spillway profile. Spillway profile, what has been constructed on site and what we have adopted, we have to basically check whether both of them are same or not.
As designed and as actually constructed.
Yeah, as actually constructed or existing on site.
So unless there is any deviation in the design, etc., I think they would have constructed as it is as per the design. Usually,
yes,
99% of the cases.
Right.
Wonderful. Very good. Very wonderful lecture.
Yes, sir.
Thank you.
Anybody else? Okay. So then, sir, thank you very much. Thank you very much, sir. Hello? Still anybody? Any queries, please? No? Okay. Sir, thank you very much, sir, Dr. Suresh Kumar Garu, for accepting our request within a short period of time and giving an important, interesting, and informative lecture, sir. So this topic is very interesting one and more required for the practicing engineers, research scholars, particularly. Without simulation, it is very difficult to complete their research work, sir. So the latest tool we have taken and explained how it can be used for different problems in civil engineering, sir. You have taken 3 different and distinct problems, sir. So very appreciable, sir. Thank you very much, sir. And thank you one and all. Now I request Dr. K. Sitaram Babu, Honorary Secretary, to propose vote of thanks.
Thank you, sir. It's a wonderful lecture, sir. I thank the chairman of the Institute of Engineers, Dr. G. Venkat Subbaya Garu, and the convener of the event, Engineer Ramma Garu, without whom probably this would not have a reality, sir. I thank them for their initiative they have taken. I also thank the past chairman, Professor Dr. Ramna Naik Garu, Vanat Garu, and Mohiddin, past joint secretary and the EC member of the Institute of Engineers current team, for having participated and part of your lecture, sir. I also thank our active members, Kondal Rao Garu and Kagender. Kondal Rao Garu is very active, interactive in talking to you and asking questions, and also doubts that we were not able to ask the questions. He asked the questions, and those doubts were clarified through his questions, sir. And thank Kondalrao Garu for that. And also thank you so much, sir, Dr. N. Suresh Kumar Garu, for having such a wonderful lecture, sir. You are a man from Usman University. I think the credentials itself speaks of high volumes of you, sir. And you are basically a man of from the water resources engineering department, sir. So, and your topic is too good, sir. And also thank some of the participants today: Bharat Garu, Sri Hari Garu, Professor Ramanujacharya Garu, Ram Prasad Garu, Ramya, Srinath, Hariyar Ayyar Garu, Prabhakar, Venugopal Rao Garu, D.K. Ashok Garu, Lakshma Reddy Garu, Manjunath Garu, Sanjeev Garu, Sri Varsha Garu, for having been part of this lecture, sir. I now hand over this to the administrative staff for national anthem, sir. We all stand for national anthem, sir. Thank you.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता। पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा। विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा। तव शुभ नामे जागे तव शुभ आशीष मांगे। गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता। जय हे जय हे जय हे जय 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 हे।
Jai Hind.
Jai Hind.
Thank you, one and all.
Suresh sir, once again, thanks to you. Chairman sir, happy journey tomorrow.
Oh, thank you very much.
Happy journey. Thank you.
మీరు వస్తారనుకున్నా.
Due to this cold and cold. Thank you. I'll try again, Matras. Thank you.
Okay, thank you.
Happy journey.
Right, thank you. Bye, sir. Thank you.